Okay, guys, we are going to start the video series over Chapter 9, which covers gases. And in this video, we are going to talk about gas pressure first. So we'll focus on the first section. We'll talk about the property of pressure for gases, and then we're going to look at different pressure units, and then we'll describe how pressure is measured. So pressure, with the symbol capital P, is defined as the force exerted per unit area. And the SI unit of pressure is called the Pascal, and it's defined as 1 Newton per meter squared. And if you expand the unit Newton, which is the unit of force, you can write that as 1 kilogram per meter per second squared. It turns out that 1 Pascal is actually a very small pressure compared to the pressures that we're used to in everyday experience. So, for example, the pressure of the atmosphere that it exerts on the surface of the Earth is over 100,000 pascals. So the SI unit of pressure is pretty small. And so we often in chemistry use a different unit, several different units. One unit is called the atmosphere. Okay, so 1 atmosphere is 1.01325 times 10 to the 5th pascals. And then another unit that we commonly use, which has to do how pressure is measured, is called the millimeters of mercury, or the unit called the torr. And 1 atmosphere of pressure is 760 millimeters of mercury. So this conversion factor you need to know. You don't really need to memorize these digits here, so you're not going to be expected to do from memory atmospheres to Pascal conversions, but you will need to be able to do millimeters of mercury to ATMs. And then you also need to know that the torr is a synonym for millimeters of mercury. So pressure is a force exerted on an area. And so in these two pictures, what we're being asked to do is to think about the force of the elephant that it exerts on the ground compared to the force that the ice skater exerts on the ice when she's on her ice skate. And so which one exerts the greater pressure? Obviously, the elephant has the larger mass. However, the elephant's feet have a larger surface area than the blade of the skate. And it turns out that the ice skater actually exerts more force because the area of contact between her foot and the ice is so much smaller than it is for the elephant, even though it has a much larger mass. In fact, the pressure is so great that it causes the ice to melt slightly, which is what allows the ice skater to glide across the surface. Let's talk about atmospheric pressure. So the way to think about atmospheric pressure is to imagine a column of air that starts at the surface of the Earth and goes all the way up to the edge of the atmosphere. Okay, so that column of air has a mass, and gravity is pulling down on it. And so it's exerting a force on a little surface area on the ground. And so that's what we call, that's what atmospheric pressure is due to, the column of air above the surface of the Earth. A device called a barometer is used to measure atmospheric pressure. It varies because the density of air varies with time, as the weather and so forth causes changes in air pressure. And so here is an example of a barometer. So you have an evacuated tube. Okay, so there's no air inside the tube, and then you dip the tube inside a little dish of mercury. And so what happens is the atmosphere pushes down onto the surface of the mercury, and that in turn causes mercury to go up inside this evacuated tube. And the pressure of the atmosphere is proportional to the height of the mercury column. Recall that pressure unit on the first slide, millimeters of mercury. You can now see why we would have such a funny unit for measuring pressure, a distance of mercury. Well, it actually corresponds to the height of a mercury column when you're using a barometer like this. And for, you know, if you take this barometer and measure atmospheric pressure, I believe at 0 degrees Celsius and at sea level, what you'll find is that the mercury column will be 760 millimeters tall. And so that's what we call atmospheric pressure. The height of the liquid column it is related to what liquid you're using. So if you use a water-based barometer, you would need a tube that was at least 33 feet tall, actually 33.9 feet tall, in order to measure the column. Now, keep in mind that that is when you have a completely evacuated tube, right? There can't be any air inside this tube at all, and the atmosphere will cause the liquid to go very far up the tube. This is in fact how a straw works. If you've ever, I'm sure you've had a beverage where you've had a straw. When you go to take a drink with the straw, what you do is you evacuate the straw. That pulls all of the air out of the tube, and then the atmosphere is what's pushing the liquid into your mouth to get a drink. The hydrostatic pressure exerted by a column of a liquid can be calculated using this formula here, where h is the height of the liquid, rho is the density, and g, the density of the liquid, and g is the acceleration due to gravity. So what we're going to do next is look at another type of device for measuring pressure called a manometer. And so a manometer is used to measure gas pressures that are not atmospheric pressure. And it typically involves, so the older kind, the kind that are kind of analog, you would use a tube like this, a curved tube, okay? And you would attach your gas vessel to this U-shaped tube. And there's different approaches. In one approach, if you've got a gas that has a pressure less than atmospheric pressure, you would use a closed tube manometer. If you had a gas with a large pressure, you would use an open-tubed manometer here. And so in this setup, the gas pressure can be measured by determining the height of this mercury column above the height here, right? The gas is pushing down onto the manometer. You've got a vacuum here. It causes the mercury level to rise, and depending on the height of that level, using the density of the mercury and the gravitational constant, you can calculate the pressure of the gas. For the open-ended mercury manometers, we've got two cases here. One where the gas pressure is just above atmospheric pressure, and one where the gas is just below atmospheric pressure. And the difference in the formulas means that you have to take into account that the atmosphere is also pushing on the mercury on this side. So to calculate the gas pressure, you have to take a difference between atmospheric pressure and then the hydrostatic pressure of the gas. For the case where the level on this side of the tube is below the level on this side, you would use a minus sign. So you would think of this as a minus height. For the case where the gas is pushing a little bit harder than the atmosphere, you would have a positive H value. And so you have the plus sign here in this equation. So you need to take into account the fact that the atmosphere is also pushing on the mercury when you go to calculate the gas pressure. So we'll put these equations to use in an example problem in just a little bit. First, I think what we're going to do is look at just simple unit conversions using involving pressures. So here we're given a pressure measured in millimeters of mercury, and we're being asked to calculate that pressure in both units of pascals and units of atmospheres. So we're going to do the millimeters of mercury to atmospheres conversion first. So 797.7 millimeters of mercury. And in every 1 atmosphere, there are 760 millimeters of mercury. Okay, so that's how we're going to do the millimeters of mercury to atmospheres conversion. So I'm getting 1.05 atmospheres out of that. And then to do the conversion to pascals, I'm going to take that 1.05 atmospheres and I'm going to say that there are 1.01325 times 10 to the 5th pascals per atmosphere. And so I'm getting 1.06 times 10 to the 5th pascals. For the follow-up problem, we're being asked to convert kilopascals back to atmospheres and then to millimeters of mercury. So we'll take the 57 times 10 to the 3 pascals, and this time we will say that 1 atmosphere on top is 1.01325 times 10 to the 5th pascals. That way the pascals cancel and we'll get the number in atmospheres. And so I'm getting about 0.56 ATMs. And then to convert that to millimeters of mercury, we'll take that times 760 millimeters of mercury per ATM. And so I'm getting 426 millimeters of mercury out of that. If we were to use proper sig figs, we'd make that 4.3 times 10 to the 2 millimeters of mercury, just because this number only has 2 sig figs. So our answer should only have 2 sig figs. Okay, so those are some simple pressure conversions. Like I said, the one that you really need to know, you need to know that 1 ATM equals 760 millimeters of mercury, and you can also call that millimeter of mercury, you can also call that the torr. In this problem, we are going to be thinking about hydrostatic pressure. So this is the pressure of a column of liquid. And the basic equation is that pressure equals the density times the height times the gravitational constant. So we're being asked to use this formula. And they want us to show that a column of mercury that is 760 millimeters of high exerts a pressure of 1 atmosphere. And so let's calculate the pressure for a column of mercury. They give us the density of mercury here. It's this 13.6 grams per cubic centimeter. The trouble is, the work that we have to do is we have to convert everything to SI units. So I'm going to be substituting in for the density, this rho, 13.6, that's grams per cubic centimeter. And I want to convert this to SI base units, or not base units, SI with no prefixes. Well, I want to convert it to the SI unit of mass, which is the kilogram, and then I want to convert it to the SI unit of volume, which would be meters cubed. So those are the conversions I need to do. So I'm going to get rid of the grams. So I'm going to say there are 10 to the minus 3 kilograms per gram. So that'll get rid of the grams. And now I need to convert the centimeters cubed. And so I'm going to say that there are 10 to the 2 centimeters per meter, but notice it's centimeters cubed, so I need to cube that conversion factor. So this right here, this is the density in kilograms per cubic meter. And then what I'm going to do is I'm going to multiply that by the height of the mercury column. So I'm substituting in for H, and I'm going to convert, in my head, I'm going to convert those millimeters to meters. So I'm going to take the 760 millimeters and divide it by 1,000 to give me the meters. Finally, I'm going to multiply by the gravitational constant, which is already in SI units. That's the 9.81 meters per second squared. Okay, and so we will do this calculation. And so what I'm getting is 101,396. Okay, and what will the units be? All right, we've canceled the centimeters cubed. Here the meters cancel, or one of the meters cancels. And then this one cancels the other one. So there's 3 meters cubed. There's a meters cubed down here, and we've got 2 meters there. So we're going to be left with 1 meter in the denominator. So it's going to be kilograms per meter second squared, and that is the SI unit of pressure. So this is 101,396 pascals, which is pretty close to the 101,325 pascals that we looked at on the first or second slide. Okay, so a column of mercury that is 760 millimeters high corresponds to 101,396 pascals. In the follow-up problem, we're being asked to compute what would be the height of a water column corresponding to a pressure of one atmosphere. So let's take the equation and we're going to rearrange it and solve for the height of the liquid column. It's going to be the pressure divided by the density divided by the gravitational constant. Okay, and so for 1 atmosphere, let's go ahead and plug in the 101,325 pascals. And in fact, instead of leaving it as a pascal, I'm going to go ahead and write it as kilograms meters per second squared. Now what we'll do is we'll plug in for the density of water, which is 1 gram per cubic centimeter. But again, we need to convert that to the SI units. So I'm going to take 10 to the minus 3 kilograms per gram. So that converts the grams to kilograms. And then I need to convert the centimeters cubed to meters cubed. So 10 to the 2 centimeters per meter. And then I need to cube that. Okay, so that's the density right there. And then lastly, I need to multiply by the gravitational constant, like that. And so we will run these numbers through our calculator. And I am getting 10.3 meters out of that, which is about what we said it was on the previous slide. Okay, so these are how you do calculations involving the hydrostatic pressure formula for a column of liquid. In this problem here, we're being asked to do some calculations for measuring the pressure of a gas using a manometer. On the left-hand side, we have a closed tube manometer, and on the right-hand side, we have an open tube one. And so for the closed manometer, the pressure of the gas is just equal to the hydrostatic pressure of the liquid column. Okay, and so that would be rho Hg. Now we don't actually have to do that. We're just simply going to take this to be 264 millimeters of mercury, and then they want us to convert that to atmospheres and then to kilopascals. So we will say that 1 atmosphere divided by 760 is 0.347 atmospheres. Okay, to convert that to pascals times 101,325 pascals per ATM. And that's going to give us 35.2 kilopascals. The number I got in pascals, I just divided it by 1,000 to give me, in my head, to give me the 35.2 kilopascals. So for this measurement, the pressure in atmospheres is 0.347 or 35.2 kilopascals. For the other measurement here, where we have the open tube manometer, we need to take into account the fact that the atmosphere is also pushing on the column of liquid. So it's the atmospheric pressure plus the hydrostatic pressure of the mercury column. And it's plus in this case because we see that the mercury column on the right-hand side of the device is higher than the column on the left-hand side. If it were the other way around, if this were 13.7 centimeters below, then we would have used a minus sign here. But since it's above, we use the plus sign. So for the atmospheric pressure, we're going to take that to be 760 millimeters of mercury. And then we're going to add to that 137 millimeters of mercury. So I'm getting 897 millimeters of mercury. We can convert that to ATMs by dividing by 760. I'm getting 1.18 atmospheres. And then we can multiply by 101,325 pascals per ATM to get it in units of pascals. And I'm getting 120 kilopascals from that calculation. Okay, so this problem illustrates how to use the manometer equations that we saw on the previous slide. So with that, I'm going to go ahead and stop this video, and we'll talk about some gas laws in the next one.